Overlay analysis, GIS in mapping water resources. An overview. Water is one of the most valuable resources on Earth, yet it is also one of the most unevenly distributed. Some regions struggle with floods, others with chronic water scarcity, and many face both at different times of the year. Understanding where water exists, how it moves, and how human activities affect it is no longer optional, it is essential. This is where geographic information systems, commonly known as GIS, play a transformative role, especially through a powerful technique called overlay analysis. Overlay analysis allows scientists, planners, and decision-makers to layer multiple types of spatial information on top of one another to uncover relationships that are not visible when data is viewed separately. In the context of water resources, this technique has become one of the most reliable ways to map, analyze, and manage surface water and groundwater systems. At its core, overlay analysis is about asking intelligent spatial questions. Where does rainfall fall most intensely? How does the slope of the land influence runoff? Which soil types allow water to infiltrate easily? How close are communities to rivers, wetlands, or aquifers? GIS makes it possible to combine all these questions into a single analytical framework, producing maps that tell meaningful stories about water availability and risk. Water resource mapping is inherently complex because water does not depend on one factor alone. Rainfall may be abundant, but steep slopes can cause rapid runoff. Flat terrain may retain water, but impermeable soils can prevent groundwater recharge. Human activities such as urban development, agriculture, and mining further complicate the picture. Overlay analysis thrives in this complexity by integrating multiple datasets into a unified spatial model. One of the most common applications of overlay analysis in water resources is groundwater potential mapping. Groundwater is hidden beneath the Earth's surface, making it difficult to assess without indirect indicators. GIS allows researchers to overlay geological formations, lineament density, fractures and faults, soil types, land use patterns, slope, drainage density, and rainfall distribution. When these layers are combined, patterns emerge that indicate areas with higher or lower groundwater potential. This approach has proven especially valuable in regions where borehole data is limited or expensive to obtain. Surface water mapping also benefits greatly from overlay analysis. Rivers, lakes, reservoirs, wetlands, and floodplains can be analyzed alongside elevation models, land cover data, and rainfall records. By overlaying these layers, GIS helps identify flood-prone zones, seasonal water bodies, and areas vulnerable to erosion or sedimentation. This information is critical for disaster preparedness, urban planning, and agricultural management. Overlay analysis is not limited to natural factors alone. Socioeconomic and infrastructural data can also be incorporated to assess water accessibility and vulnerability. Population density, proximity to water sources, irrigation networks, and industrial zones can be layered with hydrological data to evaluate water stress and demand. This integrated perspective supports more equitable and sustainable water management decisions. One of the greatest strengths of GIS-based overlay analysis is its ability to support evidence-based decision-making. Instead of relying on assumptions or isolated observations, planners can visualize complex interactions across large areas. Governments can identify suitable locations for new wells, dams, or water treatment facilities. Environmental agencies can prioritize conservation zones and protect critical recharge areas. Communities can better understand their exposure to water-related risks, such as droughts or floods. The rise of remote sensing has further enhanced overlay analysis in water resource mapping. Satellite imagery provides up-to-date information on rainfall, vegetation health, surface water extent, and land use changes. When combined with GIS layers, remote sensing data allows for continuous monitoring of water systems over time. This dynamic capability is especially important in the face of climate change, where historical patterns are no longer reliable predictors of future conditions. Climate variability has intensified the importance of overlay analysis. Changing rainfall patterns, rising temperatures, and increasing extreme weather events are reshaping water availability worldwide. GIS helps scientists model different scenarios by overlaying climate projections with hydrological and land use data. These models can inform adaptation strategies, helping societies prepare for water shortages or increased flood risks before crises occur. Despite its strengths, overlay analysis is only as reliable as the data and assumptions behind it. Poor quality datasets, outdated information, or inappropriate weighting of factors can lead to misleading results. This is why transparency, validation, and local knowledge remain essential. Field data, expert judgment, and community input should complement GIS analysis to ensure realistic outcomes. Another important aspect of overlay analysis is its accessibility. Advances in open-source GIS software and freely available spatial data have democratized water resource mapping. Researchers, students, non-governmental organizations, and local governments can now conduct sophisticated analyses without relying solely on expensive proprietary tools. This accessibility is empowering communities to take an active role in managing their water resources. As water challenges grow more complex, the role of GIS overlay analysis will only expand. From groundwater exploration in rural regions to flood risk mapping in megacities, this technique bridges science, technology, and policy. It transforms scattered data into actionable insight, helping societies move toward more sustainable and resilient water management. Overlay analysis is not just a technical method. It is a way of seeing water systems as interconnected parts of a larger environmental puzzle. By revealing hidden relationships between land, water, climate, and human activity, GIS offers a clearer path toward protecting one of our most essential resources. What we choose to do with this knowledge will define the future of water security for generations to come. Support our platform, Onyx Geospatial Solutions, by liking, commenting, and sharing our posts.